last thing that we want to talk about in this chapter is something called enthalpy. And enthalpy is represented by delta H RXN, so delta H of the reaction. And if the reaction is exothermic, we will have a negative sign. If it is endothermic, we will have a positive sign. For a exothermic reaction, we are releasing thermal energy in the environment, because enthalpy of the reaction is the amount of thermal energy that flows through a process at constant pressure. In other words, it's whether heat is given off by the reaction or heat being absorbed by the reaction. Again, we said for exothermics, we release energy into the environment, like when our methane gas, when we have methane gas and it is combusted by oxygen and it gives us heat to power our oven or our home. Endothermic reactions, however, absorb heat from the environment, and so they have a positive sign. So we can talk about how much heat is associated with the complete combustion of 1.18 times 10 to the 4th grams of propane in this case. And propane is found in the little tanks at your local gas station or your grocery store, and it's used to power our grill, right? So we have 1 mole of propane producing 2,444 kilojoules of energy. The fact that it's a negative enthalpy means that this reaction is releasing energy into the environment, which is good. That's why we need it to grill. The heat that it gives off will cook our steak, right? So let's see that if we had 1.18 times 10 to the 4th grams of propane, how much heat can we get out of it? Okay, well, this is 1 mole of propane gives us this much energy. So we can't say it's not 1 gram of propane gives us this much. So we have to convert to moles, right? So 1 mole of propane gives us 44.11 grams. That's just the molar mass of that, right? And now we know for every 1 mole of propane, we have 2,044 kilojoules of energy. Okay? So then our grams cancel, our moles cancel, and we're left with kilojoules. And we get an answer of negative 5.47 times 10 to the 5th kilojoules. So whenever we burn this much propane, 1.18 times 10 to the 4th grams, we end up harnessing this much energy. All right, what about when we have ammonia reacting with oxygen according to this balanced equation? We have a enthalpy of negative 906 kilojoules. Because it's negative, it's telling us it's exothermic. So calculate the heat in kilojoules associated with the complete reaction of 155 kilograms of ammonia. So we have 155 kilograms of ammonia. We want to convert this to grams because we want to use the molar mass to go to moles, right? So we have 1 kilogram is equal to 10 to the 3rd grams. Now we can use the molar mass of ammonia. There is 17.04 grams of ammonia for every 1 mole of ammonia. Finally, we can use our balanced chemical equation here to figure out the ratio of our enthalpy to our mole. So it looks like we have 4 moles of ammonia here give us negative 906 kilojoules of energy. It's not 1 mole because we're looking at this number here, this coefficient. So 4 moles of ammonia give us negative 906 kilojoules of energy. And so we end up getting negative 206 times 10 to the 6 kilojoules of energy if we had 155 kilograms of ammonia. Okay, go ahead and give this a try. What mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat? And the second part is what mass of carbon dioxide is produced. Butane is found in your lighter fluid, just like propane is found in tanks in your grocery store to power your grill. So all these chemical reactions have meaning behind them. They're used in your everyday products. So go ahead and try to figure this out and then replay the video to see if you got the correct answer. Now, this is a little bit working backwards from what we had. At first we were given the mass and we were asked to figure out the energy produced based on our enthalpy of the reaction. But this time we are given the energy produced and we are asked how much butane we need and how much carbon dioxide do we produce. So no problem, we just start with what we're given as always and we can work from there. So we have 1.5 times 10 to the third kilojoules of energy, and we look and we see that for every 1 mole of butane, we get negative 2,658 kilojoules of energy. So since kilojoules is on the top, kilojoules is going to go on the bottom. So gives us 1 mole of butane. Okay, now we don't stop there because we want to know the amount of grams. And how do we go from grams to moles? From moles to grams, we use our molar mass. And our molar mass of butane is for every 1 mole, there is 58.14 grams of butane. And so this gives us negative 33 grams of C4H10. But don't report it like so because we want to take the absolute value of that. Since this is mass, there is no such thing as negative 33 grams of butane. There's 33 grams of butane. Okay, so that's what you want to report your answer as. Now, what mass of carbon dioxide do we produce if we combust this reaction? No problem. We start again with what we're given. And we say, okay, we have 4 moles of carbon dioxide give us this much of energy. So that's our conversion factor this time. So we get 2,658 kilojoules of energy, and we produce 4 moles of carbon dioxide. All right. And now we want to convert to grams. So we use the molar mass of carbon dioxide, which is 44.01 grams per mole. And so we end up with 99 grams of carbon dioxide. So you see you can go back and forth using the conversion factors, using your balanced chemical equation. No matter what you are given, start with what you're given and use dimensional analysis to get your answer.